Good afternoon. I'm Edward Valentini, and I'm happy to be here today to be able to share with you some of my experience and excitement in working with LLVM. A little bit about me. I'm originally from New York. I moved about 6 years ago to San Francisco, where I worked on a couple of startups for a while, and I'm currently an iOS engineer at Fitbit. I've always been fascinated with compilers and how they work, transforming your source code into machine language. It really feels like some kind of black magic. It's kind of like you have a bread machine. You stick in all these ingredients like flour and eggs, and out pops this freshly baked loaf of bread. Today, I would like to demystify compilers for you and show you how you can work with LLVM from your favorite programming language, which, if you're here, I assume is Swift. OK, so today, I want to review the phases of a compiler. I want to talk about what LLVM is, what parts of a traditional compiler does it replace or augment, and then we're going to invent our own language called Calc, which is a very simple language for evaluating arithmetic expressions. In particular, then we'll look at something called LLVM IR, which is an intermediate assembly-like representation, which is what we're going to use to generate. And then once we have that IR, we'll take a brief look at some optimizations, and we'll look at target code generation. And I hope you guys had some coffee at the last break, because it's a very code-intensive talk. So here we go. Traditionally, a compiler will start by reading in the source language and split that text into tokens. So that's done in the lexer. Then the tokens are fed into the parser, whose job it is to build something called an AST, an abstract syntax tree. At this point, there's typically some type checking going on, and then you have your intermediate code generation, optimization, and finally, an output generated in machine code. LLVM is a suite of tools and libraries for performing the middle to back end of the compiler process. It's used for generating an intermediate code called LLVM IR, and that representation has a very strong ability to perform optimizations. And unlike a traditional compiler, which might only be able to generate code for one particular target, LLVM supports many targets for machine code generation. LLVM is written in C++. It has C bindings. And as you know, you can't access C++ directly from Swift, but you can access C. However, doing that from Swift would not be the most pleasant experience. In fact, you might become very sad dealing with all those unsafe pointers. Fortunately for us, there's a great open source library called LLVMSwift, written by Harlan Haskins and Robert Widman, which wraps the C interface for LLVM in Swift and completely Swiftifies the experience. And so we're going to use this for our examples. So the best way for me to illustrate how to make a toy language is just by example. So here you can see we have a very simple language. You can see that it resembles C in many ways. The first thing you might notice is that on my variable A, I don't specify a type because I decided in this language all types are doubles, just to make things easy. I also support a print statement because, for debugging, it just makes debugging easier. And if you notice, if you're familiar with C, you notice that the print statement looks very similar to the printf statement in C. And that's because on the back end, I'm simply taking everything that's in between the parentheses and feeding that to printf. And more about this later. But you can see that, and one other thing is, just for fun, just to add a little bit more excitement, I added a ternary operator, like your poor man's if then else. And we'll see why I did this later. But other than that, you can see that the language is very simplistic. We have no type declarations, no ability to declare other functions, no loops. That's it. So the structure of a Calc program is basically you have your main block, and it's a sequence of statements. So how did I get started? Well, OK, the first thing we have to do is take that source text and split it into tokens. So what we want to do is read in one character at a time. And basically, you have like a large switch statement and state machine that detects if that character is a complete token, starts a new token, belongs to the previous token, or ends a token. So I declared all my tokens in a Swift enum, which is very perfect for this job, because as you see, some tokens, like the identifier and the number, have an associated value. For those you want to know, for example, the identifier, you want to know the name of it. A number, you want to know its value. And some don't have associated types. I'll show a bunch of code snippets, and when I show the ... that's just been stuff that's been truncated, I'm only showing you the most interesting parts. So in the Lexer, you can imagine we have this big loop. It's going through the source text, one character at a time. And for example, once you come across a token, here I'm just showing you the simple ones. It's one-character tokens. If you come across, for example, a semicolon, you advance the index, return a semicolon. And this is how we basically tokenize our input. The parser is repeatedly going to be asking the Lexer for tokens. It's going to keep on saying, give me the next token, give me the next token. And it's going to try to make sense of these tokens and fit them into some kind of construct. And that construct is the AST, the abstract syntax tree. The AST is in turn made up of the basic building blocks of the language. For example, the statement, the expression. And so if it's the Lexer's job to turn sequences of characters into tokens, then it's the parser's job to turn sequences of tokens into nodes in the AST. So take, for example, this statement A equals B plus 3. This is specifically an assignment statement. We see that the assignment statement is made up of an identifier and an expression. And the expression, in turn, is made up of an identifier, an operator, and a number. And the leaves of this tree, notice, are all the tokens of the language. And you can see a small snippet from my AST definition as well. If you look at the definition for expression, you'll see that it's recursive. And it's great in Swift. You can have the indirect keyword, which gives you a heap allocated reference type. So you can see here we have two types of statements. We have the assignment statement and the print statement. And remember, the structure of a Calc program is just a sequence of statements. So our AST is really just a sequence of statements. And statement list is just a wrapper around an array of statements. OK, so this type of parser is called a recursive descent parser. Typically, you'll have a method for each type of object that you have in your AST that knows how to parse that type of object. And we saw that there's two types of statements, the assignment and the print. So if we're in the process of asking the Lexer for tokens, and we're not in the middle of parsing something else, let's say we're in between statements right now, and you get a print token, then we're going to assume that we have a print statement, and we're going to try to parse the rest of the print statement, the open parentheses, the quotes, until the semicolon. And if we're doing that, and for some reason we run into an unexpected token, that method will throw an error. If we didn't have a print statement, then we have to have an assignment statement. And the assignment statement starts with an identifier. And if we don't see an identifier, then we know that there's some error. So we have something unexpected. And that's why we throw an unexpected token error. If we did get the identifier, we try to parse the rest of that statement. And so we're basically consuming that token. That just means advance to the next token. And then we consume an assignment token, which is the same thing as consume token, but it throws an error if that token wasn't an assignment. And then we try to parse the expression. And if we can get through all of that, then we know we have a valid assignment statement, and we can just return it. So semantic analyzer, I really just put in here for completeness. We don't have one in the Calc language. Everything is a double, so there's not really any type checking to do. But But I just wanted to put it in here to illustrate that if we did have multiple types, then this is the phase where you would go through and check that. Imagine that our identifiers are in green, are doubles, and that the number 3 is defined as an integer. Then as you're walking through the AST, you could notice that, and you could throw some type of error, like type mismatch or something. So now we have this AST, and our ultimate goal is to be able to generate machine code. So the first thing that we want to do is we want to walk through this AST and generate an intermediate representation for this. So let's talk about LLVM IR. LLVM IR is an intermediate representation which is kind of in between your source level language and assembly. It's a powerful form that lends itself to many optimizations, and many of the optimizations available to LLVM take place on this intermediate format. The format itself has 3 representations: a text-based representation, which we will be working with, mostly used for debugging. There's also a binary bitcode representation used for saving to disk. And finally, an in-memory representation. So what is single static assignment? It's a type of intermediate code where variables can only be assigned once. So effectively, you have an infinite amount of registers. The actual register allocation is done later at the code generation phase, which kind of makes sense because different hardware will have different amounts of registers. And so in LLVM IR, the module is your top-level container. A module is a collection of global variables, functions, external references, and other data. Then you have your functions, which specify a return type, parameters, and then a function definition, which is comprised of a set of basic blocks. And what are basic blocks? They're parts of code that have only one entry and exit point. So no branching or looping. There's no other way the execution can go through other than by single-stepping through the code, through the instructions. More about LLVM IR. Everything is in a flat global namespace. To avoid symbol clashes, you'll often see mangled names. For example, if you look at this function in Swift, if you tell the Swift compiler to emit IR, you will see a mangled function name. That's because everything is in a flat namespace. So you have global variables that start with an ampersand, locals with a %. You have your usual suspects, integers of any bit size. 1 bit is a Boolean. Doubles, you can have pointers. You can also make custom types, which we won't get into. But so that's a very quick overview. And let's dive in. So let's start with something even more simple than hello world. We'll get to hello world in a few slides. Our main entry point is a global main function. And then you see our a first basic block, and it returns a function that returns void. So let's see how we would build this, how we would access the machinery of LLVM from Swift to emit this IR, which does absolutely nothing. So there's some boilerplate you need to do. First, you need to get a reference to a module. You need to set up a builder object. The builder object is very similar to a drawing context in that you can add functions, variables, you can add basic blocks to the functions, and you can move the cursor around and then emit more instructions there. So this is how we would do this very basic snippet of code that does nothing. OK, now let's talk about allocating memory. So we have these 2 lines of code, A equals 3 and B equals A. And we want to see what is going to happen under the hood. So what we're doing here is we are allocating space on the stack for a double. And we write its address into the variable named %a. We then store the constant value of 3 in the memory location pointed to by the address in variable %a. Notice the second operand of the store instruction is a double star because we need to dereference that address. And then finally, we load the value, which is a double, pointed to by the address in variable %a into variable %b. And how we use LLVMSwift to do this is we just build an allocate instruction and get a reference to a constant and build a store, and there you go. One last thing, this allocate instruction is for allocating values on the stack. The memory is automatically freed when the function exits. It's completely possible to have manual memory allocation, and many types use that. And you would just use malloc and free the same way you would do in C. We won't talk about any of those types, though, here. And now we finally get to Hello World. So the thing about Hello World is what we want to do is we want to see how we can call an existing function. We get a reference to a global string variable, Hello World, and a function printf. And we tell the builder the name of the function. We define the return type and the argument types, and we then provide. But notice that we do not add any basic blocks, and we do not provide a function definition. And then we build a call instruction to the function, and we give it the arguments. If I try to compile this, well, if I output the object code, I will be able to do that. But then if I try to link it and generate an executable, it won't work. It'll tell me that there's an undefined symbol, printf, until I link it with libc or on libsystem on the Mac, which is what I do at the last stage. So with this information, we can now call any function, not just printf, but we can call any function that's available in any library. One of the things I could do to add to this language is I could add support for sine, cosine, tangent, a lot of other mathematical functions, and then just link them later with libm. OK, so remember several slides ago when I said I added that ternary expression just for fun? Well, now we've arrived at that fun. The Phi Node. The Phi Node is a single static assignment concept which allows you to express branching, looping, and some other constructs. Here in the entry block, we have a floating point comparison, which is trying to compare the value in register A with the constant 7. And then what the ONE means, it means for ordered not equal. So if the value in A is not equal to 7, then it's going to set the variable B to 1. Otherwise, it'll be 0. And then we see that the next line, it checks variable. The variable C is a 1-bit integer, an I1. And it checks that. If it's 1, it goes to the true block. If it's 0, it goes to the false block. Those two blocks, in turn, just branch to the Phi block. The Phi block, then, this is the most interesting part, it registers as a double, but it takes its value based on where the control flow came from. So if the control came from the true block, the value is going to be set to 12. If it came from the false block, then the value is going to be set to 6. So this is how you can do loops and branching with LLVM IR. That's why I added the ternary expression, so I could show you this Phi node. And finally, we see how we could create this construct in Swift. The new things here are just the floating point comparison. And here you can see an example of like the moving the cursor. You can see that we have a reference to the current function. We append our basic blocks, and then we can, as we're emitting instructions, we can position our cursor where we want to emit those instructions. OK. Finally, to give you a taste of just some optimizations, there are literally hundreds of optimizations that you can use. You can even write your own optimization passes. Sadly, though, not in Swift yet. Those need to be in C++. But optimizations can be done at the module level or at the function level. So what I want to do is show you the Swift code that you would use to just apply a basic instruction combining optimization, which what that does is it performs some algebraic simplifications. And that's an optimization that works on functions. And basically, I'm getting a list of all the functions in my module and applying that optimization to them. In a Calc program, you only have one function, the main one, because we don't allow you to do it, but just so you would see how you would do it. And so I want to show you the effect that it has on the LLVM IR. If you look at this snippet of IR generated from our running example of the Calc program, notice on the left we have the entry basic block, which is not the complete LLVM IR that would be generated by that, but so you can see it's the part where we allocate the double on the stack, we store the 4 in the a pointer to 4 in the register, and so basically the first 4 lines. The compiler, the optimizer, is able to figure out that this is entirely deterministic at compile time. There's no way that 4 is ever going to be equal to 7. So it is able to figure out that that entire 4 lines of code is always going to be true. And when you run the optimizer, you see that it basically just sets the constant true because it's able to figure that out. Finally, code generation. These are the targets for which you can generate machine code. If you call a machine generator without any arguments, it just generates code for the current machine that you're running on. And here I had it. You could have it emit LLVM bitcode or just object code. Here I just chose to emit a .o file. And finally, the last step, if I run the compiler, I'll get a .o file. I link it, and you can see I link it with libsystem on a Mac, and it outputs the example binary. And if I run it, it gives me the output that I expect. And I know this has been a very quick and whirlwind tour of LLVM, but I hope it was enough to demystify it for you so that you guys can hack around with it yourselves. Thank you.